Okay, problem 2-4. This problem has to do with freefall. A rubber ball is dropped off a cliff, and this time there's actually air drag. So the air drag has a magnitude of BV squared. And so for part A, we have to label any forces that are acting on the ball. So here's the ball, and there's a downward force of gravity, which is mg, but then there's also an upward force of the air drag, which is bv squared, but then it's negative because it's going against it's resisting against the force of gravity. So that's your answer. Okay, part B of this problem asks whether the acceleration of the ball increases, decreases, or remains the same as it approaches its terminal velocity. The answer is that the acceleration actually decreases because the ball goes faster and faster due to mg. So ball, because mg causes the ball to go faster. But then as mg causes the ball to go faster, there's also an increase in air resistance. And then this means that the total downward force decreases as the ball approaches terminal velocity. So mg stays the same and the air resistance increases. Causing a total decrease in downward force. Okay, so part C. Part C asks us to write a differential equation to find the instantaneous speed v of the ball at any time, t. So we know the force on the ball is gravity minus air resistance. So that's, the force is gravity minus the air resistance. And then we also know that F equals ma. It's a differential equation, so we're going to try to get dv dt. And we can get that because A is also dv dt. So then F equals m dv dt, and we can set these two equations equal to each other. So we have m dv dt equals mg minus bv squared. Try to get dv dt alone, so we have dv dt equals mg minus bv squared over m. These cancel, so we're left with dv dt equals g minus bv squared over m as our answer. Okay, on to part D. Part D asks us to find the terminal velocity speed v. To do this, we must notice that when an object is at its terminal velocity, its acceleration is 0. This means that the upward and downward forces must cancel each other out. And we know that the upward and downward forces are downward as mg and upward as bv squared. And they have to equal each other. So we know b as a constant, so now we can just solve for v with this equation. So we get mg over b equals v squared, and then we just get v equals square root of mg over b as our answer. Okay, part E asks us to determine the energy dissipated by the drag force during the fall if the ball is released at height h and reaches its terminal speed before hitting the ground. So all this is simply asking is, what is the difference in energy between the potential and final energy? We can say that the change in energy is equal to the max potential minus the final kinetic energy at any time. So the total energy is the max potential mgh minus the kinetic energy at any time, which would be 1/2 mv squared. So recall that our answer from part D is the square root of mg over b. So we can actually use this in our answer, in our equation, to solve for our answer. So we get total energy is mgh minus 1/2 m, substitute part D answer, which is square root mg over b squared, so that just cancels out here. So then we have E equals mgh minus 1/2 m mg over b. Now we can factor out a g and an m and a g. So we have total energy equals mg. We're left with h minus 1/2 m over 2b. And that's our answer.